All right, so this is example one, and the situation that I'm given in this problem is just a description of a real method that astronomers use and can use to calculate distances to faraway objects. So the idea, the method is called parallax, using parallax angles, and the idea is that if you measure the angle from Earth to a nearby object, here it says it's a star. Uh, that if you take that same observation, measure the angle 6 months apart, then you'd have these two observations that have made, and we could consider those to be opposite ends of a triangle, or 2 points of a triangle, and the object you're trying to estimate the distance to is that third object. So if you can use those angles, you wouldn't actually. What I don't like about this diagram is the angle it has labeled here as the parallax angle. This is not the angle that you would be able to measure because you wouldn't be over at that star. You're here at Earth, so you'd be measuring these two angles right there between the sun and the object. And those angles are going to be really close to 90 degrees. But if you have precise enough instrumentation, you can measure those angles. And if you have that, and we know the distance the from the Earth to the Sun is about 150 million kilometers. We can use that information to estimate distances. Now that does have some limitations, depending on how far away the objects are. That if they're too far away, this method won't work. We even our most precise instruments can't use this method. But if they're near enough to some of the closer nearby stars, we can use this method pretty well. So that's kind of the theory behind it. So for this particular case, there's going to be kind of a problem that comes up a little bit later that we'll look at in just a moment. But the situation that we're given here, of course, the distance from the Earth to the Sun varies from depending on the time of year, but it's about 150 million kilometers average. And they're saying that this parallax angle is 7 degrees. Really, what they should say, like, there's no way we'd be able to measure that. They really ought to be telling us the angle that we'd be measuring right here from Earth's perspective. But I don't. That's the angle that they give us. So at any rate, how do we approach a problem like this? Well, it might you might think, well, we've got sort of this isosceles triangle we could kind of look at, but we can actually break this up a little bit simpler. We can create a right triangle based on this diagram. If we just ignore that bottom half of the isosceles triangle, what we get is this, and I'm just going to pop it out here. Essentially can just create this triangle right here with a height of 150 million kilometers. This angle on the left side is 7 degrees, and just think about this as a right triangle. So essentially, I can just pull out a right triangle from this diagram and just work with my rules of right triangles. So in this case, that would be the sine of an angle is opposite over hypotenuse, and I can set up my equation like this. So I get a quickly adjust here. The sine of 7 degrees would be equal to 150 million kilometers over the hypotenuse, which is the long end of the triangle here from the Earth to that distant star. And if we just rearrange the equation for h, then we get a distance of 1,230 million miles, which is supposed to be a star, but that distance would put it somewhere between Jupiter and Saturn here in the solar system. So I don't really think these numbers quite make sense, but that's the method and the that we would use to approach a problem. And again, this is a valid method. The numbers here that they present us with this problem are not really reasonable. Obviously, we can't have a star that's uh, somewhere in the solar system, but that in principle, if we had some more accurate angle measures here, we could that is how astronomers can judge distances, or one of the ways that they can judge distances to